describing the gas, we assume that it follows the like quantopic formula, and also that because of this, that air is quasi-static in our assumption.
Why do you believe other assumptions, like the thermal assumption, are incorrect in this phenomenon? Could you?
Because the rate of air injection is fast such that there's like less heat exchange, so
could I ask
is
what
not
is your rate of air expansion? Do you have any calculations?
Oh, you mean like the rate I push air into the?
No, like the rate at which the air bubbles like expands or.
Yeah. So for the, I believe it's around like 5 ml per. Sorry, 0.5 ml per second.
And you believe that's with this.
Yeah, because like we didn't use a faster air injection method because then like.
So I agree with you. I believe that if we use the faster air injection rate, then it would be okay to use other assumptions. But for this rate, I believe that the polytropic assumption is correct. So, in your calculation, did you take into account the adhesiveness of the fluid with the walls of the container?
Sorry, the what?
The adhesiveness, like.
You mean the wetting of your walls? The
Yeah,
wetting of the.
yeah.
So we believe that is negligible, and perhaps like it could be proved. For example, so if you see like these where we colored the fluids, when it rises, there might be some fluid which are sticks to the walls, which causes the walls to look somewhat darker. But here we can see that the walls has sort of the same like clear color as the top part, which is not wetted. So we believe that there's like minimal wetting on the surface of the container.
So you mentioned that you use silicone already, right?
Yes.
And what was the material of your container?
Just plastic.
Right. So did you calculate like using formulas, like what the adhesiveness would be, like numerically?
No, but I agree that
it's like
it could be calculated.
Right. So I agree with you. I feel like it would be nice if you had calculated numerically what the number would be, so that you could sort of prove that it is insignificant. What do you believe is the effect of surface tension on the initiation
of the initiation? So the surface tension would sort of cause the shape of the bubble to be varied. So here, so in this case, we could use the Young-Class equation to sort of approximate for the shape of the air bubble here. So yeah, but then we didn't really do a quantitative calculation for this because we believe that the edge effect of the container would cause the bubble to have a different shape, which is hard to account for, and also because the point at which we inject the air here cannot be perfectly flat to the bottom surface of the container, so it will have some slight effect on the shape of the bubble.
So you mentioned that if the bubbles are too small, they would float.
It's not too small, but if the frequency is too slow, so according to this equation.
So you, sorry to interrupt you. So you believe that the frequency of the air injection is an important parameter.
No, the frequency of the oscillation.
Right. So I'm talking about like the
injection rate.
Right. Injection rate. Right. So you in the bubble initiation.
Yes.
Phase, right?
Yes.
What do you believe the parameters are? Right.
So what affects this? So
because could I clarify my question? Because what I understood from your presentation, I believe that you took into account the rate of air injection, but not the, not the, I want to say like the volume of air that is injected.
No.
Perhaps if the volume, in my opinion, if the volume is too small, it wouldn't be large enough to form an air bubble. Yeah.
I agree with you. So but for our theory, we assume like quasi-static assumption for the description of the air. So the speed of the air injection would not really matter unless it's really quick, which makes the cause-and-effect assumption not valid.
So what do you believe would happen if we use a not different assumption for the injection of air? What if it wasn't constant?
So I suppose we need to use some more complex equations to describe the motion of the air, which has velocity when it is injected out of that very small hole.
So moving on to the next point, if we graph viscosity over shear stress, I believe that we have two types of materials, where some materials are viscotic, where they have an increase in viscosity, and some materials are thixotropic, where they have a decrease in viscosity. So I believe that silicone oil is a thixotropic fluid, and basically what it does is that when shaking it, it sort of decreases.
I don't believe that this effect would be so high because if you consider the shear between the walls and the this layer, it's actually it oscillates. So that I don't think that the shear would be large enough to have a significant effect on the value of the viscosity.
I agree with you. I believe that we don't have homogeneous viscosity all over the. Because
I believe it is.
I believe there's more internal friction near the walls.
Yes.
So I believe that we have inhomogeneous.
I believe that is negligible and doesn't really affect the bulk motion during the steady state.
Okay. So you mentioned that the syringe used to inject the air had a very small diameter, right?
Yes.
So what did you presume would happen if the syringe had a larger diameter,
So I mean, we just have to control for the rate of air output of the from the syringe. So I suppose if the syringe shell had a different shape, it perhaps could have some surface tension effects on the shape of the bubble. It was something like this, but
okay?
I don't believe it has a very large effect on the main levitation phenomenon.
Right. So in my opinion, I agree with you completely, but I feel like we should I believe that the mass flow rate of the air injection is important. Needs to be taken into account. So let's move on. What do you believe are the limits of this phenomenon?
You mean between when it can and cannot occur?
Right.
So
I feel like you also mentioned that
here are some of the two sort of possible ways that it can fail. So firstly is the Rayleigh-Taylor instability for low accelerations. So where we can see the classic thing where when a higher density fluid on a lower density fluid will have some concentration which grows exponentially, and on the other end we have different rates, which are the standing rates that form on the liquid surface.
So could you give me any numerical for what frequency do we have Faraday waves or roughly? What does it depend on?
For the Faraday waves, we used this sort of diagram to find the regions where it is stable and unstable. But this is an assumption for liquids which have for infinitely large volume of container and infinitely deep fluid. But we think that this can give a good approximation for the.
What about different densities of fluid? Did you try the different fluids?
Densities.
Yeah. Did you try different fluids? And is there a density at which we can't see bubbles anymore because the fluid is too light? Or
we didn't vary the density of the fluid, but I suppose it will have some effect on the appearance of these because the rho L appears in all these terms. But I suppose if it's just